Okay, let's dive right in. Buried deep inside pretty much every phone, every laptop, every car, there's a story of a hidden war. Now, this isn't a war fought with soldiers, but with code. It's a fundamental battle of ideas that has shaped our entire digital world, and today we're going to uncover its secret history.
To really get what's at stake here, just imagine this for a second. You're driving, and the music app on your car's big screen glitches out. So what if that one little bug could not only freeze your music, but also shut down your speedometer, your engine, your brakes, absolutely everything? The design philosophy that stops this from happening is really the heart of our story.
All right, so the story really starts with the kernel. You can think of it as the absolute core of an operating system. It's like the brainstem of your device. It controls everything. And for a long, long time, there was basically one main way to build it, a design that was really powerful, but also, dangerously fragile.
And that design is called the monolithic kernel. The name kinda says it all, right? Monolithic, like one giant single stone. All the essential services, I'm talking about the code that talks to your graphics card, your Wi-Fi, your hard drive, it's all packed into one enormous, interconnected program. And it's all running in the most privileged, most powerful part of the system. And that is the conundrum. See, because everything is sharing the exact same space, there are no walls between them. So a bug in your printer driver isn't just a printing problem anymore. No, it can accidentally mess with the memory that the file system is using, and that can cause a total catastrophic failure. This is the classic blue screen of death we all know and, well, we know it. One tiny crack can bring the whole building down. So, by the late 1980s, engineers knew this was a huge problem. As our computers got more and more complex, the risk of one of these total crashes just kept growing. And out of that challenge, a radical, almost elegant new idea was born for how to build a kernel. It was called the microkernel, and the philosophy behind it was just beautiful in its simplicity. Do the absolute bare minimum inside that privileged kernel. Just have it manage memory and handle the most basic communication. Everything else, drivers, file systems, all the networking stuff, all of it would get pushed out into its own isolated little user space program.
Now, this slide is the perfect way to picture the difference. A monolithic kernel, it's like one giant fortress. If an enemy gets past one section of the wall, the entire castle is compromised. But a microkernel, that's more like a city full of separate protected buildings. A fire in one building is contained. It doesn't burn down the whole city. Makes sense, right? And the promised benefits of this new way of thinking were just huge. A crashed Wi-Fi driver? No problem. The system could just restart that one little service, and you probably wouldn't even notice. Need to update a part of the system? You could just swap it out, kind of like changing a light bulb, instead of having to rebuild the entire thing. In theory, it was safer, way more stable, and a lot more flexible. It was supposed to be the future.
But you know how it goes. Elegant theories often run into some harsh realities. This beautiful idea of the microkernel was about to go through a serious trial by fire, because in the real world, it had one major, almost fatal flaw.
They were slow. I mean, painfully slow. Remember how all those services were now their own separate programs? Well, to get anything done, they had to constantly talk to each other by sending messages through the kernel. That process, which we call inter-process communication, or IPC, it just created a massive amount of overhead. Every simple little task required all this extra work, and performance just plummeted.
And this huge performance problem, well, it fueled a ton of skepticism. There was this rising star in the programming world, a guy named Linus Torvalds, and he was famously unimpressed. He saw all this focus on architectural purity as just a distraction from what really mattered to users, speed. To him, anything that tried to mix these ideas was just marketing fluff.
This whole conflict really got personified in one of the most famous debates in computing history. On one side, you had Andrew Tannenbaum, the creator of the Minix microkernel. He was arguing for his beautiful, secure, forward-thinking design. And on the other side, you had Linus Torvalds, the creator of Linux, arguing for a pragmatic, monolithic design that was just flat out, fast, and worked right now. It was the visionary versus the pragmatist.
And for a while there, it really looked like the pragmatists had won. Monolithic Linux basically took over the world. But a new generation of engineers just refused to let this beautiful idea of the microkernel die. They knew the benefits were real. They just had to solve that performance problem.
And they did it. A German computer scientist named Johann Liedtke. He looked really closely at why those early microkernels were so slow, and he realized the idea wasn't flawed, the implementation was. His work led to a whole second generation of microkernels, like the L4 family, that were built from the ground up with one thing in mind: speed.
So how'd they pull it off? I mean, it was through some absolutely brilliant optimizations. They figured out how to make that message passing process 10 times faster. They created a direct process switch to basically cut out the middleman. They treated performance not as some afterthought, but as the central goal of the entire design.
And this brings us right back to our car. The reason your Spotify app can't possibly crash your speedometer is because a lot of modern cars run on a high-performance microkernel, something like QNX. It uses that core principle of isolation to keep the super important safety-critical stuff completely separate from the other apps. The redemption was complete. The ideal work.
So, after all that, who won the kernel wars? Was it the visionary or the pragmatist? Well, the surprising answer is actually written into the code of the very device you're watching this on right now.
Yeah, it turns out the real winner was a compromise. Both Windows and Mac OS use what we now call a hybrid kernel. They took the core idea of a microkernel. I mean, Apple's kernel literally has the mock microkernel inside of it. But for performance reasons, they pulled a lot of the services, like graphics drivers, back into that privileged kernel space. So they get some of that modularity and safety, but with the speed of a monolithic design.
When you look back, you can just see this incredible evolution playing out over decades. You start with those simple monolithic designs in the 70s, then you get the revolutionary ideas of the 80s, the pragmatic backlash of the 90s, and then finally, you land on the specialized success and the hybrid compromises of today.
But here is the final and, in my opinion, the coolest twist. Remember Minix, Tannenbaum's microkernel that pretty much lost the public debate to Linux? Well, get this. A version of Minix is secretly one of the most widely deployed operating systems on the entire planet. It's running deep inside the Intel management engine on millions and millions of processors, managing the chip itself. The failed idea was so reliable and so secure, it was chosen to run in the most trusted part of your computer. How wild is that?
So the crucial point is this. The kernel wars never really ended. That tension between purity and pragmatism, between security and speed, it's still here and it continues to drive innovation. It teaches us that sometimes the most important outcome of a big debate isn't about deciding who won, but about the incredible progress that comes from the fight itself.